What's the magic word? A control theory of LLM prompting. Aman Bhargava 1, Cameron Witkowski, Manav Shah, Matt Thompson. Abstract. Prompt engineering is crucial for deploying LLMs, but is poorly understood mathematically. We formalize LLM systems as a class of discrete stochastic dynamical systems to explore prompt engineering through the lens of control theory. We investigate the reachable set of output token sequences RYX0 for which there exists a control input sequence U for each Y in RYX0 that steers the LLM to output Y from initial state sequence X0. We offer analytic analysis on the limitations on the controllability of self-attention in terms of reachable set, where we prove an upper bound on the reachable set of outputs RYX0 as a function of the singular values of the parameter matrices. We present complementary empirical analysis on the controllability of a panel of LLMs, including Falcon 7b, Llama 7b, and Falcon 40b. Our results demonstrate a lower bound on the reachable set of outputs RYX0 WRT initial state sequences X0 sampled from the Wikitext dataset. We find that the correct next Wikitext token following sequence X0 is reachable over 97% of the time with prompts of k less than or equal to 10 tokens. We also establish that the top 75 most likely next tokens, as estimated by the LLM itself, are reachable at least 85% of the time with prompts of k less than or equal to 10 tokens. Intriguingly, short prompt sequences can dramatically alter the likelihood of specific outputs, even making the least likely tokens become the most likely ones. This control-centric analysis of LLMs demonstrates the significant and poorly understood role of input sequences in steering output probabilities, offering a foundational perspective for enhancing language model system capabilities. 1. Introduction. LLMs pre-trained on unsupervised next token prediction objectives exhibit unprecedented dynamic reprogrammability achieved through prompting, often referred to as zero-shot learning. These capabilities appear to emerge as the model's size, training data, and training time are scaled. The dynamic reprogrammability of LLMs is akin to the adaptable computational capacities observed in biological systems. This feature finds applications across domains such as machine translation, code generation, and chatbots by et al. 2022. A rigorous understanding of the prompt's influence over LLM generation would be of great utility for understanding LLMs and building more robust and capable systems leveraging LLMs. Strategies for controlling pre-trained LLM generation today fall into three broad categories. 1. Input optimization, prompting, adjusting the input tokens, e.g., rewording the prompt to improve subsequent text generation. 2. Model optimization, adjusting the weights of the network, e.g., fine-tuning RLHF to improve model behavior during inference. Post-processing, adjusting or re-ranking generated text, surrogate ranking algorithm. Of all these approaches, input optimization, i.e. prompting, is the least invasive and lowest cost method and the least understood. Prompt optimization is also deeply connected to the zero-shot capabilities of LLMs, the mysterious emergent capabilities of LLMs such as problem-solving, knowledge retrieval, reasoning, and apparent general intelligence. With such a view, we seek to characterize the controllability of LLMs via prompting. 1.1 Contribution. We formalize LLM systems in the mathematical framework of control theory in Section 3. Our analysis focuses on the reachable set of outputs RIX0 for an LLM system. The reachable set is a fundamental concept in control theory that underlies notions of controllability, stability, and observability, cf. Appendix A. The reachable output set RYX0 is the set of output sequences Y for which there exists a control input sequence U that steers the LLM from initial state X0 to output Y, cf. Definitions 3.11. Our analytic results in Section 4 prove an upper bound on the contents of the reachable output set for a self-attention head as a function of the singular values of its parameter matrices. Since self-attention is the only component in a transformer block where significant information is exchanged between token representations, this bound provides a foothold for analysis of LLM controllability from the perspective of mechanistic interpretability. Moreover, this bound represents a necessary condition for an output to be in the reachable set. Our empirical results apply state-of-the-art prompt optimization techniques, Section 5.1, to demonstrate a lower bound on the contents of the reachable output set for a panel of LLMs, including Llama 7B, Falcon 7B, and Falcon 40B. Specifically, we sample initial states x0 from the Wikitext dataset and probe the reachable output tokens y under length-constrained control input sequences u less than or equal to k. The length constraint k is highly relevant for optimal control of LLMs, as prompts with fewer tokens require fewer computation and memory resources. We find that the reachable output set contains the correct next Wikitext token following x0 over 97% of the time, with prompts of k less than or equal to 10 tokens. We expand our analysis of the contents of RI x0 by sampling target output tokens y based on the LLM's initial estimate of output likelihood PLM yx0. We find that the top 75 most likely output tokens y are reachable at least 85% of the time, with prompts of k less than or equal to 10 tokens. Intriguingly, some tokens drawn from the set of least likely outputs are controllable to the most likely output with k less than or equal to 4 control input tokens. Our results suggest that prior likelihood-based metrics, such as cross-entropy loss, cannot guarantee exclusion from the reachable set, emphasizing the gap in our current understanding of LLM systems and control. Implications of our results and open questions in LLM control theory are further discussed in Section 6. 2. Related work. Much of the work on prompt optimization is concerned with finding prompts that induce higher LLM performance on fill-in-the-blank or close tasks. One can frame a range of tasks including knowledge retrieval, reasoning, and sentiment analysis, Wang et al., 2023, as fill-in-the-blank tasks. Knowledge retrieval. The Titanic sank in the year Mask. Answer 1912. Reasoning. A is taller than B. B is taller than C. Is A taller than C? Answer. Mask. Yes. Sentiment analysis. I am sad today. The sentiment of the previous sentence was mask. Answer. Negative. Notably, there is some freedom in the bolded prompt text that surrounds the question to convert it into a fill-in-the-blank task. As it turns out, the prompt tokens have a large effect on LLM performance. Modern prompt optimization algorithms generally consist of 2 iterated steps: a sampling step where new prompts are generated and a testing step where the utility of the new prompts is evaluated and the best are selected for the next iteration. Algorithms primarily differ in the sampling procedure, where various heuristics may be used to pick high-value swaps. Overall, AutoPrompt and its derivative algorithms have been the most numerically successful prompt optimization methods, with the greedy coordinate gradient (GCG) algorithm having state-of-the-art performance. The AutoPrompt family, AutoPrompt pioneered the current wave of prompt optimization. Shin et al. Propose a prompt optimization technique and demonstrate its effectiveness for engineering prompts to improve LLM performance on knowledge and sentiment analysis tasks. At its core, the AutoPrompt algorithm leverages gradient information at the token embedding layer to inform iterative token exchanges within the prompt. This method was extended in Zhou et al. 2023 as the greedy coordinate gradient (GCG) algorithm. Taking inspiration from adversarial examples, Zhou et al. Applied this AutoPrompt variant to generate jailbreak prompts that cause aligned LLMs to generate objectionable content. Other prompt optimization methods. Other investigations on LLMs as prompt optimizers and further analysis of manual prompt optimization are informative, but do not exceed the AutoPrompt family's performance. Some other methods include GBDA, an approach based on the Gumbel softmax reparametrization, the PEZ algorithm, which directly optimizes embeddings via gradient information, and Fluent Prompt, which differs from AutoPrompt by incorporating Langevin dynamics. Despite the variety of alternatives, GCG retains state-of-the-art performance. Control theory for LLMs. To our knowledge, the only other work to date on the controllability of LLMs is Soato et al. 2023. Soato et al. Analyzed the controllability of LLMs in terms of meaningful sentences, defined as the sigma algebra generated by snippets of text written on the Internet. Their empirical analysis revolves around demonstrating that LLMs are capable of attributing meaning. The theoretical analysis of LLM controllability is limited to meaningful sentences, eliminating the possibility of out-of-distribution inputs and outputs. These restrictions render their results challenging to leverage toward a practical understanding of LLM controllability. we situate our work as a practically oriented exploration of LLM controllability. Motivated by challenges in developing LLM systems, we do not eliminate meaningless sentences from the state space or input space. We aim to establish a rigorous, general framework for understanding LLM systems and controllability that is amenable to the development of theory and practical engineering insights on systems design. 3. Control theory, for LLMs. Control theory originates from the study of automatic control systems in engineering. It seeks to understand how a plant system can be influenced toward a desired state using a control signal, often in the presence of disturbances and uncertainty. Control theory is central to a variety of engineering problems, from electrical engineering to autopilot to telecommunications to manufacturing. Surprisingly, control theory has also been highly applicable to a diverse range of scientific disciplines. Analyzing systems through the lens of controllability has proven fruitful for generating insight into biological systems such as cell signaling pathways and neural networks, the economics of central banking, and controlling the spread of infectious diseases. One of the central benefits of studying systems via controllability is that a range of questions and problems naturally emerge from the framing. When is control possible? What is the cost of control? How computationally intensive is control? These questions are both practically useful and often lead to fundamental insights about the nature of the system in question. To develop a control theory of LLMs, we provide fundamental abstract definitions of systems and control, Appendix A. We apply them to define LLM systems and outline specific canonical control concepts and problems such as controllability and reachability that arise naturally for LLM systems. Language model notation. We denote a causal language model using PLM. PLM maps from an ordered list of tokens from a vocabulary set V, e.g. x in Vn, to the probability distribution over the next token xn plus 1x in V. We use V-tries to denote the set of all possible sequences of any length composed of tokens from V. The addition operator indicates the concatenation of token sequences. Bolded lowercase variables, e.g. x equals gonais 1xn, denote token sequences, while unbolded lowercase variables refer to individual tokens, e.g. x in V. The length of a token sequence is denoted x. While LLMs are at times leveraged in a manner that masks the iterative aspects of generation, the reality is that token generation and externally imposed control input sequences are generated and processed sequentially, leading to non-trivial system dynamics. Several key differences remain between LLM-based systems and systems typically modeled through ordinary differential equations, ODEs, which have long been a cornerstone in the study of continuous time dynamical systems. 1. Discrete state and time. LLM systems operate on sequences of discrete tokens over a discrete time set, in contrast to the continuous state spaces and time sets studied in classical control theory. 2. Shift and grow state dynamics. Whereas the system state in an ODE-based system has a fixed size over time, the system state x of t for LLM systems grows as tokens are added to the state sequence. 3. Mutual exclusion on control input token versus generated token. The LLM system state xt is written to one token at a time. The newest token is either drawn from the control input ut or is generated by the LLM by sampling ext plm xxt. This differs from traditional discrete stochastic systems, where the control sequence and internal dynamics generally affect the state synchronously. We begin by rigorously defining LLM systems with user input, drawing from the abstract mathematical definition of a system, Definition 7. Definition 1, LLM system with control input. An autoregressive LLM system with control input, C equals V PLM, consists of T equals N, the time set is the natural numbers, X V, the state space consists of all possible token sequences of any length drawn from V. We denote the state at time t as xt equals x0t, xt, u equals v xt. The input takes values from the vocabulary set V or null. Phi x times t2x. The transition map is C equation. Note that the general multi-step transition map phi xt u t plus n can be achieved by iterating equation 1 for control sequences u defined over the interval t plus n. hxtr equals xt minus rt xtt. The readout map returns the most recent r tokens from state xt. We note that this LLM system definition is generalizable to a variety of LLM augmentation, including chain of thought, retrieval augmented generation, and chatbot interaction. For example, chain of thought is equivalent to sampling the readout map hxtr at time t u plus x0 plus r for prompt u and initial state x0. A similar formulation may be applied to LLM systems endowed with programmatic tools, e.g. Patil et al. 2023. In definition 1, we assume that the control input gets to decide whether to yield token generation to the LLM ut equals geet or override the LLM and add some token ut equals is8 to the state x of t. This assumption generally holds when building LLM systems, though it may not hold when using existing systems, e.g. via non-streaming API. When discussing finite-length control inputs, e.g. the family of k-long input sequences u in vk, the value of u at k is implicitly JEK unless otherwise stated. While next token generation xp plm xxt in equation 1 is probabilistic, we may render the system determinist sampling with zero temperature greedy decoding. The greedy decoding assumption provides a foothold to analyze the reachable sets and controllability of LLM systems without invoking notions of stochastic control, as in Sivaramakrishnan et al. 2023, Soato et al. 2023. Moreover, it remains connected to temperature-based stochastic decoding strategies as a limiting case of temperature-based sampling, as zero-temperature sampling. We now extend definition 10 to define output controllability for LLM systems. Definition 2, LLM output reachability. Output token sequence Y in VR is reachable from initial state x0 in VChan for LLM system VPLM if there exists some time t and input ut in ut that steers the LLM from initial state x0 to output y equals h of t r at time t. We disregard the trivial solution wherein the control input u.t overrides the LLM to force the state sequence to take on the desired output value y. The reachable output set definition for LLM systems follows from definition 11, definition 3, LLM reachable output set. The reachable output set from initial state x0 in VChan for LLM systems sex equals VPLM is denoted RYX0 and consists of all reachable outputs y in VChan from initial state x0. Output controllability for LLMs follows from definition 13. Definition 4, LLM output controllability. An LLM system equals VPLM is output controllable if, for every initial state x0 in VTrame, the reachable output set RYX equals V3. The turn-based nature of writing to the LLM state sequence xt invites the question of whether the prompt u should preempt the imposed state x0 or come after the state 1. We focus our efforts on cases where u comes before imposed state sequence x0 due to its importance for developing system prompts and controlling text completion-based generation, where the desired output is x0 plus y for some desired continuation of partial string xo. Due to the costly nature of long prompts, we are especially interested in the existence of prompts u with minimal length u. Definitions 3 and 4 form the basis for our control theory of LLMs. While amenable to analytic analysis as in Section 4 and Soato et al. 2023, empirical analysis of the reachable set and controllability is challenging due to the intractable size of VStry. We propose the following statistical measure of controllability for practically assessing the controllability of an LLM system, WR a dataset D under prompt length constraint. Less than or equal to K. Definition 5 K-F controllability. Consider a dataset of state output pairs D equals XI0 YI I and N. An LLM equals VPLM is K-F controllable WRD if, for at least a proportion of 1 minus XI0 YI in D, the following condition holds, see equation. Where RKYXI0 is the reachable set of outputs, as in definition 3 under the constraint that prompts U must have length U less than or equal to K. Our empirical work in section 5.2 explores K-I controllability WRT initial states X0 sampled from the Wikitext dataset. While empirical analysis of LLM controllability is challenging due to the lack of apparent structure in LLM dynamics and the combinatorially large state space, we may still experimentally establish the existence of optimal prompts U that elicit a given output and thus establish a lower bound on the content of the reachable set. Meanwhile, our theoretical work in Section 4 establishes upper bounds on the content of the reachable set for self-attention. We hope these complementary approaches aid in unifying our understanding of LLM systems. For mathematical analysis on the controllability of self-attention. Self-attention is a central component in modern transformer-based language models. Introduced in Vaswani et al., self-attention is the primary component in transformers where token representations exchange information. Both situations are reasonable in developing LLM systems. U preceding x0 may arise when prompting an LLM to complete a partial string x0. U preceding x0 may arise when prompting an LLM in the presence of an imposed system prompt x0. Therefore, how an initial state x0 is interleaved with control input u is largely a design decision. Definition 6. Self-attention. Self-attention CUX WQ WV is a map from Rn din Rn's doubt, where n is an arbitrary number of input token representations, each of dimensionality din, and doubt is the dimensionality of the output token representations. See equation, where xp denotes element-wise exponentiation of the matrix entries, wq, wk and rdk, wv and rdine doubt, q at xwq, kxwv, and d is a diagonal positive definite matrix defined as C equation, where 1 n tie 1 is an n's 1 matrix of ones. Note that the parameters and operation of COX are independent of the number of token representations n. Self-attention may be applied to discrete token sequences x in VVAX, provided that each token xi in x is first mapped to a representation in the input dimension with some embedding map e v rn. We are interested in the reachability of output token representations, where we partition the input x in R of k plus m times din into an k times din block of control input representations u and an m times din block of imposed state representations x0, cf. definition 1. We also partition the output equals x in R k ham din into a corresponding k ham doubt matrix u and an m times doubt matrix y. Motivated by the architecture of transformer-based language models, we seek to characterize the reachable set of output representations y in RKYXO under imposed input representations xro and controllable input representations u, where u consists of k token representations. While the reachable set is now a set of continuous valued output representation matrices in Rm ham din, we may readily adapt definition 3 to define the reachable set for these conditions. Theorem 1. Condition for exclusion from the reachable set. A desired output representation y ties in Rm's doubt must be excluded from the reachable set RKYX0 if the following condition holds for any row I. See equation, where ob equals max j of uj for rows uj of u, ob x equals max j xj0 for rows xi0 of x0, q and sub k are the maximum singular values of wq, wk respectively. Q dixx is the ith element on the diagonal of dxx, which is given by C equation, where qx equals x0 wq, kx equals x0 wk, and vx equals xwv. The proof of equation 5 is provided in Appendix B. Intuitively, this condition arises when the output representation yx that occurs when only the imposed state x0 is fed into the transformer is too far away from the desired y for the control tokens u to steer the output to yxb. The ability for the control input u to nullify the impact of yx equals kex x0 on the output scales with the number of control input tokens k. A control input with many tokens can dominate the influence of x0 by reallocating attention away from the component of the output yx that arises from x0. A notable insight from the proof is that one may decompose the output of attention into components that arise largely from different parts of the input. While there are cross terms in the attention matrix, these amount to only a positive scaling factor applied to the independent components like yx. Thus, we have an analytic bound on the reachable output set for self-attention. See further commentary in Section 6. 5 experiments. To gain a practical empirical understanding of the reachable set RKYX0, we probe the existence of optimal prompts U across datasets D of initial state desired output pairs, X0 Y pri. We scope our experiments to study immediate control, i.e. we check the LLM output after Y tokens are generated, where the control input U is prepended to the imposed state X0. Moreover, we focus on the case of controlling the LLM system to produce a single output token Y in V under some constraint U less than or equal to K. This single-step control renders the problem of gauging reachability computationally tractable and is a fundamental step toward understanding the iterated dynamics of LLM systems in terms of reachability and controllability. We leave the exploration of reachability and controllability under an extended time horizon, e.g., chain of thought, chatbot dynamics, tool-wielding LLMs, and under the requirement of multi-token outputs Y to future work. 5.1 Methods. We apply prompt optimization algorithms to establish the existence of optimal prompts U of length k that steer the LLM system from initial state x0 to output y for some dataset D of initial state output pairs. In general, prompt optimization algorithms accept a token sequence and a loss function on said token sequence, along with a specification of which tokens are manipulable. The output of a prompt optimizer is a manipulated token sequence, i.e., optimized prompt, designed to minimize the loss. We apply two computational methods to generating optimal prompts: greedy back generation and greedy coordinate gradient. We found that greedy back generation performed best for short prompts k less than or equal to 3 tokens, while GCG was the best performing algorithm for prompts of 4 or more tokens. To our knowledge, our greedy back generation algorithm is novel. For brevity, we place the full description of the algorithms and our parameter values for the two algorithms in Appendix C, as the specifics of the algorithms are not the main contribution of this work. We focus on understanding the content and structure of the reachable set of LLM system outputs RKY of x0, particularly under a constraint on the number of input tokens k. To determine which output tokens are reachable under varying input sequence lengths, we apply an incremental prompt lengthening procedure when searching for optimal prompts on some dataset D. Algorithm 1, backoff prompt require state output token sequence x0y, LLM system sex PLMV. 1. For k from 1 to 3 do 2, uk equals greedy back generate x0y. 3. Return uk if it steers sex from x0y. 4. End for 5. For k and do 6, uk equals greedy coordinate gradient x0y. 7. Return uk if it steers from x0y. End for 9. Return failed to establish reachability. 5.2 Results. Our results revolve around the reachable set RKYX0 for state sequences sampled from the Wikitext dataset. Results were computed for a panel of models, including Falcon 7b, Falcon 40b, and Llama 7b. Falcon 7b results are showcased in this section, while additional plots and results for Falcon 40b and Llama 7b can be found in Section D. We applied the same back-off prompt strategy, Algorithm 1, to determine k-ALA controllability for all experiments, varying the specifics of the dataset D for each experiment. Ground truth reachability. We established the reachability of the ground truth next token y preceding state token sequence x0 in Wikitext. In our tests on a dataset of 5,000 state output sequences with states of length 8-32 tokens, we found that the true next token y is reachable over 97% of the time across all models with a prompt of length k less than or equal to 10. Figure 1, top left. Plots and supplementary figures for Falcon 40b and Llama 7b controllability T ground truth Wikitext outputs can be found in Section D.1. Figure 1, main experimental results on k-L controllability of Falcon 7b. Top left, k-EV values for Falcon 7b on ground truth target token y cry. 97.16% of the instances were solved with a prompt of length k less than or equal to 10. Top right, k-ALT values for reaching the top 75 most likely outputs y's for each x0. The top 75 targets were reachable at least 89.39% of the time with a prompt of length k less than or equal to 10. Bottom right, prior likelihood rank of target token y of prompt versus required prompt length to elicit y fry. Target tokens were sampled uniformly from the least to most likely token. Top 75 reachability. To explore the reachable set RKYX0 beyond the ground truth of Wikitext outputs, we generated a synthetic dataset of outputs by sampling 25 Wikitext sequences x0 and selecting the top 75 most likely next tokens according to the model itself PLM-YX0 as the target tokens, Figure 1, top right. We found that the top 75 output tokens were reachable over 85% of the time for all models with control sequence length k equals 10. Supplementary figures including results for Llama 7b and Falcon 40b on k-MIC controllability with respect to the top 75 most likely output tokens can be found in Section D.2. Uniformly sampled target outputs. To maximally push the bounds of the reachable set within our single output token scope, we created another synthetic dataset where the target output token y site was sampled uniformly from the highest likelihood next token to the lowest likelihood token. Although the overall K-minus score was relatively poor, only 46.43% reachable with K equals 10 for Falcon 7B, we were intrigued by the near-uniform relationship between prior token rank, based on PLM YX0, versus the required number of prompt tokens. Figure 1, bottom right, plots the relationship between prior target token rank based on PYX0 and the required prompt length K to elicit the prompt. While over half were unreachable, the remaining reachable tokens appear uniformly distributed in terms of required prompt length, regardless of rank. Supplementary figures analyzing the K-L controllability of Falcon 7B with respect to uniformly sampled target outputs Y can be found in section D.3. 6. Discussion. We proposed a control-theoretic framework for understanding language model prompting, orienting our investigation around the reachable set of outputs RKY of XNARO. We proved a bound on the reachable set of outputs for self-attention in terms of the singular values of its weight matrices, and we established fundamental results on the reachability of correct next tokens, according to Wikitext. We expanded the scope of this investigation by probing the reachability of tokens assigned high likelihood by the LLM itself, and tokens assigned minimal likelihood by the LLM itself. Bounding the reachable set for self-attention is deeply related to the mechanism by which consistent representations are formed for multi-token generation. Steering a language model to generate a desired token sequence requires that the control input induce a token representation in the rightmost token such that the next token prediction logits PYU plus X0 achieves a desired value. Moreover, generated tokens are fed back into the model, and their representations must be steered as well to control iterated generation. Self-attention is the primary mechanism by which the token representations exchange information, making the reachable set of output representations across multiple tokens in X0 for self-attention a fundamental part of LLM control theory. Our empirical results suggest that there is far more to the reachability of a given output than just prior likelihood or the prior rank the LLM assigns to a given token. Although prompt optimization-based K-8th controllability experiments are only able to provide a lower bound on the content of the reachable set, the ability to frequently control even the least likely token to being the most likely token with just a few input tokens is intriguing. We believe this result indicates the importance of further investigating the reachability and controllability of LLMs, particularly for developing capable and reliable LLM systems. Our investigations provide an entry into the understanding of LLM controllability via prompts. However, a comprehensive understanding necessitates extending our exploration into diverse regimes. Exploring the controllability with longer prompts and longer questions, base token sequences, will be pivotal. Equally important is the study of diverse models to verify the generality of our findings. Moreover, the direct comparison of controllability scores of different model families is challenging since family uses a different tokenizer. The Llama family tokenizer, for instance, has a vocabulary of 30,000 tokens, whereas the Falcon family has a vocabulary of 65,536 tokens. Further work is required to robustly compare controllability across models. An intriguing observation from our study is the log linear relationship between prompt length K and controllability fraction ordered. See Figure 2 in Appendix D. While this is compelling within our studied domain, it raises the essential question: is this relationship robust outside our current explorative scope? Unearthing universal scaling laws in LLM controllability would not only inform practical control applications, but also open the door for theoretical insight into the nature of LLM behavior. The progress we have made, both in understanding the bounds on self-attention controllability and the empirical measures of K-C LLM controllability, underscores the potential of this control-theoretic framing for studying LLMs. Below is a non-exhaustive list of open problems in LLM control, all stemming from the framing in Section A. Control properties of chain of thought. Chain of thought is a powerful technique where LLMs are allowed to generate intermediate tokens, i.e., thoughts, between a question and an answer. The control properties, e.g., stability, reachability, of systems leveraging these techniques are of great interest for understanding and composing systems of LLMs in the real world. Distributional control. To what extent can we control the output distribution of a language model PLM, yx0 plus u, to a desired distribution py? Computational cost of control. What are the performance characteristics of LLM? Control regularized by computational cost? Learnability of control. To what extent can LLMs learn to control each other? Work such as Zhou et al. 2023 showed that LLMs are capable of human-level prompt engineering, but it is unclear how well an LLM can learn to control another when explicitly optimized on the objective of LLM control. Controllable subspaces. In the control of linear dynamical systems, it is known that uncontrollable systems are often coordinate transformable into a representation where a subset of the coordinates are controllable and a subset are uncontrollable. Sontag 2013. We have shown that controllable and uncontrollable components naturally emerge for self-attention. Heads in Section 4. Can this be generalized to transformer blocks with nonlinearities and residual streams? Composable LLM systems. One of the greatest boons of control theory is the ability to compose control modules and subsystems into an interpretable, predictable, and effective whole. The composition of LLM systems, potentially with non-LLM control modules, is an exciting avenue for scaling superintelligent systems. A abstract systems and control theory background. This section aims to provide an overview of fundamental control theoretic concepts from an abstract perspective. We primarily draw from Sontag, Kalman et al., and Ogata. Diverse definitions of system or machine exist in the literature, all representing the same core concept but varying in mathematical details. We offer the following high-level definition based on Sontag. Definition 7. System. A system or machine, T equals Tx U phi, consists of T, the time set along which system state evolves, X, the state space, U, the input space, phi, X times UT2, X, the transition map. A system may also be equipped with an output space and readout map, YH, Y the output space, H, X time T, Y the readout map. In other words, at time T and T, the system state takes on values X and X and the control input takes values U and U. The system evolves over time with the transition map phi X UTT that returns the new state value Xi and X at time TT. A system can also have a readout map HXUT that produces the output value Y given the current time, state, and input value. An input U and U defined over interval T may be said to steer the system C equals TXU phi from state X0 to state Xi if X equals foot UTT. A wide variety of systems are expressible within this framework. We obtain discrete time dynamical systems for T equals Z plus. Continuous time dynamical systems emerge for T equals R plus. Note that we assume that the system SES is time invariant. Its dynamics phi do not change as a function of time. This assumption is widely applicable and is often made in the literature to simplify definitions and discussions of systems. Reachability is a core control theory concept and central to defining controllability. At their core, definitions of reachability revolve around the existence of control inputs U and U that steer the system from a starting state X0 and X to some desired states. Following from Kalman et al., Sontag 2013, we define state reachability as Definition 8, state reachability. State X in X is reachable from initial state X in X for system equals TXU phi. If there exists some time T and control input in U such that U's T steers the system from state X0 to state X at time T. We may use this definition of state reachability to define the reachable state set for some initial state X0 in X. Definition 9, reachable state set. The reachable state set from initial state X0 in X for system C equals TXU phi is denoted R of X0 to X and consists of all reachable states in X from initial state X0 CF. Definition 8. For systems with readout maps H, notions of output reachability arise naturally. Note that state reachability is neither necessary nor sufficient to guarantee output reachability. Definition 10. Output reachability. Output Y in Y is reachable from initial state X0 in X for system sem T XUYH if there exists some time T and control input U in U such that U steers the system from state X0 to output Y in time T. Definition 11. Reachable output set. The reachable output set from initial state X0 in X for system SAO T XU phi YH is denoted RYX0 and consists of all reachable outputs Y in Y from initial state X0. Definition 10. A system is controllable when the reachable set extends to the entire state space. Practically speaking, this implies that one can steer the system from any initial state to any desired state. Definition 12, state controllability. System sex Txu phi is state controllable if, for every initial state x0 and x, the reachable set Rx0x. Definition 13, output controllability. System set Txu phi yh is output controllable if, for every initial state x0 and x, the reachable output set Ry equals y. A range of fruitful questions stem from these definitions. If there is a cost associated with control inputs u and u, e.g., power constraints, length constraints, what is the minimum cost of control? What is the minimum time required to get from the initial state to the desired final state or output? If the system is not completely controllable, under what conditions is it controllable? Under which readout maps is a system output controllable? B. Proof of self-attention controllability theorem 1. Note, key terms for the proof are introduced in section 4 surrounding theorem 1. Specifically, the definition of self-attention mechanism KEX, the control problem setup, and the reachable set RKYX0 are required background for this proof. Proof. For each token representation matrix Q, K, V in R of K plus hems, we denote the first K rows corresponding to U using U as a subscript, like QU. The remaining M rows corresponding to X0 are denoted with subscript X, like QX. Let A be the exponentiated query key outer product matrix with the following block structure. See equation. We apply a similar quadrant decomposition to D, defined initially in equation 4. See equation, where the quadrant demarcations in D follow from equation 8. We may now express the self-attention mechanism output representations Y as see equation. We begin by stating the equality between the desired output YC and the true system output from equation 10. The final bound in equation 5 of theorem 1 is derived by isolating terms depending on control input U, bounding them, and expressing that bound as a condition for achieving equality between the desired output Y and the true system output. See equation. We may immediately bound the magnitude of the rows of U as the matrix D-1XU has rows that sum to less than 1. It represents one quadrant of the row-wise softmaxed attention map, which has rows that sum to 1 by construction. Therefore, each row yiu of U lies within the convex hull, defined by the row vectors viu of Vu. Recalling definition 6, Vu equal WV. Let OBU equals max j uj for rows uj of U. We can bound the norm of each viu and Vu with the maximum singular value of parameter matrix WV, denoted 7q. Refer to Chapter 5 of Calafiore 2014 for an overview of singular values. Thus, we may bound each viu less than or equal to hu. By the properties of convex hulls, each row of U must inherit this upper bound on magnitude to retain feasibility. Wada yiu and OU 17. Refer to Chapter 8 of Calafiore and El Gaoui 2014 for a detailed explanation of convex hulls and their properties. While yx in equation 11 may appear to depend only on imposed x0, the denominator term d-1x contains influences from U. Let us split the denominator term dx equals plex xu, where dxx depends solely on the imposed input x0. dxx is defined in equation 6. Let dxu be defined as see equation. Recall equation 7, which defines yx, the output of CUX if only x0 is input. Let us express the condition in equation 11 using yx to disentangle the influence of the control input, see equation. Observe that the rows of yx and yx are positively scaled versions of each other because the denominator matrices are all positive and diagonal. Applying the bound in equation 13 using row-wise notation, see equation. Using the same singular values reasoning as in equation 13 to bound the unknown denominator term dixu, which is the only term still dependent on the control input U. See equation. Achieving this minimum value will minimize the value of yix by maximally scaling down yx. The maximum value for yix arises when dixu is minimized, e.g. to 0, resulting in yix equals grid yix. Therefore, the value of yix is constrained linear scalings between this minimum and this maximum. If every scaling violates the inequality in equation 16, then the system is strictly controllable. Therefore, if yix less than or equal to 0 for some row I, following inequality is met, the output y to x is strictly unreachable under imposed input representations x0 and control input u. See equation. See prompt optimization algorithms. Greedy back generation. While testing all prompts in VK is intractable for K-Day1, it takes only V forward passes of the network to compute the loss on Y induced by all possible single-token prompts U in V. Our greedy back generation algorithm leverages this fact to generate prompts U in VK one token at a time, working backward sampling the ith greedy optimal single-token extension U equals arg maxu PLM YU plus U plus X of the current prompt U in Vi-1. Algorithm 2, greedy token-wise prompt generation. See algorithm. This method is optimal for K equals 1 prompt token in V and generally outperforms GCG for short prompts of length K less than or equal to 3. Computing one additional prompt token takes roughly 1 to 4 minutes when using an NVIDIA A100 80GB GPU with a 7 billion parameter model, and 5 to 20 minutes on two NVIDIA A100 80GB GPUs with a 40 billion parameter model. Greedy coordinate gradient GCG. The greedy coordinate gradient algorithm, presented by building off the work of, is the state-of-the-art method for optimizing prompts. Starting with a random prompt of length k, the algorithm generates a batch of alternative prompts. Each member of the batch swaps a random token in the current prompt with a promising alternate token. The value metric for a swap is given by a first-order approximation of the change in loss, L equals CE loss Y PLM YU plus X, with the embedding of each token in U. Algorithm 3. Greedy coordinate gradient. See algorithm. This method outperforms all other methods we tested for prompts of length K3. We use a batch size B equals 768, sampled from the top K sub equals 128 token replacements at each index, and iterate for T equals 34 iterations. For each instance, this optimization took roughly 2 minutes for the 7 billion parameter models on a single A100 80GB GPU, and 4 to 8 minutes for the 40 billion parameter model on 4 A100 80GB GPU. D supplementary figures, optimal control prompts Deep 1, ground truth controllability results. This subsection includes supplementary figures for the controllability of Llama 7B, Falcon 7B, and Falcon 40B ground truth target outputs from Wikitext. For each initial state sequence x0, the target output y is the token immediately following x0 in Wikitext. We measured the K-S controllability of each of the 7 billion parameter models with a dataset of 5,000 state output pairs, while we used a dataset of 500 state output pairs for Falcon 40B. Figure 2 shows each model's log-spaced K-S curves on the Wikitext dataset, revealing a log-linear relationship between maximum prompt length K and the fraction of uncontrollable initial state target output pairs, x0 y. We visualize the relationship between prompt length and the prior cross-entropy loss of each LLM on predicting the target output y given the state sequence x0, i.e. minus log PLM y x0 in Figure 3, where we find it difficult to predict the required prompt length from the base loss. Finally, Figure 4 shows a histogram of the tokens in the optimized prompts generated in the ground truth K-S controllability experiments on Wikitext. Figure 2. Log-spaced main results of K-log controllability. Interestingly, the relationship between K and log RUS appears roughly linear for each question length in the regime studied. Top left, K-log RUC values for Falcon 7B. With K equals 10 control tokens, 97.16% of the target outputs were reachable. Top right, K-log values for Llama 7B. With K 10 control tokens, 98.64% of the target outputs were reachable. Bottom right, values for Falcon 40B. With K equals 10 control tokens, 97.00% of the target outputs were reachable. 0, 2, 4, 6, 8, 10 prompt length K 10 2 10 1 log portion incorrect og epsilon Falcon 40 K log. Controllability on Wiki 500 question length 8 question length 10 question length 16 question length 22 question length 32. D2 top 75 Wikitext controllability results. This subsection includes supplementary figures for the controllability of Llama 7B, Falcon 7B, and Falcon 40B on the Wikitext dataset, where the target output token Y for a given initial state token sequence x0 is sampled uniformly from the top 75 highest probability tokens, as determined by the language model itself, PLM-YX0. Specifically, the dataset D consists of 25 unique initial state token sequences x0 sampled from Wikitext, each replicated 75 times for the top 75 most probable subsequent tokens Y, PYX0. This procedure yielded a dataset of 1875 initial state target output pairs, X0, Y, for the 7 billion parameter models. Due to the computational requirements for the 40 billion parameter model, the number of unique initial state token sequences was decreased to 10, resulting in a dataset of 750 initial state target output pairs. The K-8 plots for each model are shown in Figure 5. On average, across the three models, the top 75 outputs were reachable 86.865%. Figure 3. Required prompt length K versus base loss on the target output L equals minus log PLM Y X low. While there does appear to be an exclusion zone in the top left-hand corner where a high prompt length is never associated with a base loss below a given threshold, base loss appears to be a poor predictor of required prompt length of the time with K less than or equal to 10 prompt tokens. Similar log linear trends were observed in the K-6 plot. Figure 6 shows the relationship between base loss and required prompt length, revealing a more dramatic exclusion zone in the top left, similar to main ground truth results in Figure 3. Finally, Figure 7 plots a histogram of the 40 most common tokens observed in the optimized control input prompts from the top 75 experiments. D3 uniformly sampled output token results. This section contains supplementary figures for K- controllability experiments on a synthetic dataset D equals X0, Y, where X0 are sampled from the Wikitext dataset and Y is sampled uniformly from the vocabulary. The uniform target output dataset D consists of 616 state output pairs. Due to computational constraints, K-MICE's controllability was only measured for Falcon 7B. Overall, only 46.42% of the target outputs were reachable with K equals 10 prompt tokens. Figure 8 visualizes the K-8 results, the relationship between base loss and prompt length, and the most frequently observed tokens in the optimized control prompts. While the exclusion zone behavior, cf. Figure 6.3, is observed in the base loss versus prompt length subplot, base loss remains a poor predictor of required prompt length. Moreover, Figure 1 reveals an even more uniform relationship between the initial rank of the target output token and the required prompt length. Figure 4 prompt token frequencies for Falcon 7B top, Llama 7B middle, and Falcon 40B bottom from Wikitext ground truth target token K- at controllability experiments. Figure 4 prompt token frequencies for Falcon 7B top, Llama 7B middle, and Falcon 40B bottom from Wikitext ground truth target token K- at controllability experiments. Figure 7 prompt token frequencies for Falcon 7B top, Llama 7B middle, and Falcon 40B bottom from Wikitext top 75 synthetic dataset K controllability experiments. Figure 8 supplementary figures on uniformly sampled target output controllability tests on Falcon 7B. Top left, K-X plot 46.42% controllable at K10. Top right, base loss versus required prompt length. Bottom, histogram of top 40 most frequent tokens in optimized control prompts. This concludes the reading of What's the Magic Word? A Control Theory of LLM Prompting on Research to You. If you would like more papers added, please leave a comment. If you would like to be notified when more papers are available, be sure to subscribe, like, and ring the bell.